Welcome to a video lecture on the electromagnetic waves and the Doppler effect, and we'll see how once again we saw the Doppler effect with sound, and now we'll see it again with electromagnetic waves, and it works in kind of the same idea, and what happens is you get this idea of a frequency shift. But we'll look at that in a little bit, and here we go. Hello, welcome to another video lecture. Here our special guest today is Mr. Andre Darian. He's going to be talking about the Doppler effect and its applications to astronomy.
Thank you very much. Thank you to Mr. Wolf for allowing me to come in and speak to you guys for a few minutes. I wanted to talk a little bit about the Doppler effect and how it's used in astronomy. Because when I get to this topic in astronomy class, I'm often surprised that a lot of students think the Doppler effect only works for sound waves. Because many of the examples we use in physics class to explain Doppler effect involve sound waves because it's easy to demonstrate. But in astronomy, the Doppler effect is very important for us to understand something about the structure of the universe and how things are in the universe. So for example, a very simple question that astronomers wanted to answer was, do galaxies move? And we used the Doppler effect to answer that question. And yes, indeed, they do move. And with the Doppler effect, we can find out how fast they are moving. Okay, I'll do a sample calculation in a few minutes just to show you how to calculate the speed of a galaxy. But just to explain a little bit something, review something of the Doppler effect, I'm going to show you something and look at what happens if to the waves as an object is moving. Okay, so I'm going to do a very simple example. I'm going to start with a bug jumping on water. Okay? So if you can imagine a bug doing jumping jacks on water, they're going to make waves, and they're going to be concentric waves. Something like this. Okay? Now, let's say that bug starts to move. What's going to happen to the waves? Okay? I'm going to erase my little galaxy here and put it back up in a second. Well, if we imagine the bug doing jumping jacks and moving, sort of like this, okay, he's going to form a wave pattern like this. And as you can notice, the waves in the front part, if he's moving in this direction, are closer together. Okay, so we'll get a shorter wavelength and higher frequency. Okay, so short lambda, high frequency. Okay, if we're back here looking at the bug, as he's moving away from us, this area, you can see there's more space between the waves. So there's a longer wavelength, longer lambda, and lower frequency. The same thing happens to light as an object's moving towards us or away from us. So if you give me a second to put up some notes. If we just take a quick look here, I just put up a very brief schematic of the visible part of the electromagnetic spectrum. So red, there should be orange, yellow, green, blue, and so on, violet. Towards the red end of the spectrum, the light has long wavelengths and a low frequency. At the blue end of the spectrum, the light has short wavelengths and high frequency. So if an object in space is moving towards us or away from us, we'll see the spectral lines, okay, that are produced by the light shifted along the visible part of the spectrum. For objects that are moving away from us, we'll see that the light is going to be shifted towards the red part of the spectrum, and we call that a red shift. If the object's moving towards us, Okay, the wave fronts are going to get closer together, and we're going to detect the wavelengths at shorter wavelengths and higher frequencies, and we would call that a blue shift. Okay, and so astronomers can determine if something very simply is moving towards us or away from us depending on where they measure the wavelength of light. So here I have a diagram, very schematic. It is definitely not to scale. This is a galaxy, and here's the Earth. And if we look at the light that's coming from the galaxy, and especially if we pass that light through a spectrometer, which will break up the light into its component colors, we'll often notice that we'll see a shift in the expected wavelengths. So for example, one of the spectral lines that astronomers look for is hydrogen, since hydrogen is the most abundant element in the universe. And in the laboratory, if we were to look at a spectra of hydrogen and look for its red line, you would measure it at a wavelength of 450 nanometers. What often happens is when the astronomer measures the light, he sees a shift in it, and it's no longer found at 450 nanometers, but it might be found at 498 nanometers. And so as you can see, there's a difference in the wavelength. And now we can apply the Doppler effect and actually use it to calculate the speed of this galaxy. And first of all, let's ask ourselves a question. This galaxy, is it moving away from us or towards us? Well, it would be moving away, and we would notice, since we're getting a longer wavelength, it's shifted towards the red part of the spectrum. Okay? And so what we would see would be something like this. We'd see the wavelengths getting longer and longer. Maybe I can try to draw that a little bit better. Okay. If we were on the other side of this galaxy, say we were in a spacesuit on the other side, floating around. Okay. Draw my big astronaut spacesuit here. Little antennas. If we were to measure the light, we would notice it blue shifted. We would see the wavelengths coming towards us with a shorter wavelength. And therefore we'd say this is blue shifted. Whereas over here on Earth, since they're seeing the light shifted towards the red part, we say it's red shifted. So now we're going to use these numbers and do a quick calculation to figure out how fast this is going. So here is the form of the equation we use in astronomy using the Doppler effect. This V is going to stand for the speed of whatever object we're looking for, in this case a galaxy, but it could be the speed of a star as well. C is always the speed of light, 3 times 10 to the 8th meters per second. On top here we have delta lambda. It's going to be the difference in these wavelengths, the difference between the stationary wavelength, the wavelength of this hydrogen light we would measure in the lab, which would be 450 nanometers, with the experimental wavelength, the observed wavelength, which is 498 nanometers. And that's going to be put up in a ratio over the stationary wavelength. Okay? So if we start to plug in some numbers, we're going to be looking for V, the speed of the galaxy. So I have V over 3 times 10 to the 8th meters per second. The change in the wavelength between 498 and 450 nanometers is 48 nanometers. And that will be over the 450 nanometers, the stationary wavelength. Okay? Well, so this ratio comes out to be 0.11. And solving for v, I just have to multiply that by the speed of light, both sides. 3 times 10 to the 8th meters per second. And that gives me a speed of 3.2 times 10 to the 7th meters per second. And if we kind of pull that out, what does that mean? That means that that galaxy is moving at 32 million meters per second. Which is about 64 million miles per hour. Okay? And so, in a very simple calculation, we can easily calculate the speed of a galaxy. This can also be used to find the speed of rotation of a star, because that's how we know, for example, stars rotate, is that when we look at one edge of the star that's turning away from us, we see the light
it's turning away, it shifts to the
red. Yeah, so if it's the part of the star that's turning away from us, if we look at a star rotating, the side of the star that's rotating away from us, we would notice the light red shifted. The part of the star rotating towards us would be blue shifted. Okay, so we can calculate the rotation speeds of stars by using the Doppler effect. There's a couple of other shifts in astronomy. Instead of using the Doppler effect and stuff, and to make astronomers sound cooler and different, we just talk about redshift. So whenever you hear an astronomer say redshift, they're talking about Doppler effect. Okay? But we use redshift has also been used to show that the universe is expanding, because again, we can measure these recessional velocities of galaxies. That kind of shift is due to the fact that space is expanding, and we call that the cosmological redshift. Then there's also gravitational redshift, which comes into play with black holes, because when an object starts to fall into a black hole, the light has to work against gravity. It actually loses energy. As it loses energy, it gets shifted to the lower part of the spectrum towards the red. So actually, if I were to fall into a black hole, this nice blue sweater I'm wearing, you would start to see it turn into a nice red sweater. But we don't want that to happen, because then it's bad news if you fall into a black hole. In fact, they have a term, and you can look it up on Wikipedia, called spaghettification. So imagine me being turned into a big giant string of spaghetti. That's what happens. So anyway, I hope this is helpful and you learn a little something about the Doppler effect. And again, I wish to thank Mr. Wolf and thank you guys for listening. Thank you very much.
So I want to thank Mr. Darian for doing that and helping me out. And just want to kind of refresh a couple of things here. So the Doppler effect, as with sound, it occurs with electromagnetic waves. And it's, once again, the shift in frequency that causes a difference. And when you have something moving towards or away, there's different types of shifts. So you get a red shift or a blue shift. Blue shift happens when you're moving towards something. It's kind of, there's that increase in frequency. So this is for the Doppler effect. There's his formulas that he uses are more attributed to astronomy, whereas we'll use something a little bit different, I think, in class. But we'll talk about that more tomorrow. So without further ado, thank you very much. Have a good night. No questions. Enjoy.